This podcast will discuss Chapter 9 in our textbook, Differences Among Groups. Our objectives for this podcast are to explain the basic ideals and statistics when comparing the differences between groups. And the other thing is we want to provide an overview of the following statistical tests: T-test and ANOVA test. So, differences in groups. We can use different statistical tests to evaluate the effects of an independent variable on a dependent variable, or multiple independent variables on a dependent variable, or multiple independent variables on multiple dependent variables. These statistical tests are different than correlational statistics because we're not looking for any kind of relationship between the variables at all. We're actually looking to determine if an experiment or a treatment or something that we've done to our groups has actually worked. And what I mean by different groups is exactly what it sounds like. We have, let's say we have 3 different groups of people that we're trying to work with. A group of, we're going to use this example in a little bit, different levels of fitness. So we have a high level of fitness, a medium level of fitness, and a low level of fitness. And we have, say, 15 people in the high level of fitness, 15 people in the middle level of fitness, and we have 15 people in the low level of fitness. Each one of those are considered a group, and then we can develop a research study to determine if there's a difference between those 3 different levels of fitness and those groups of individuals. And there are different types of statistical tests that we can use to determine that for us. The first type of statistical test we're going to talk about is what's called a T-test. That's called a student T-test. If you watch that goofy video I gave you to watch back in week 4, there was a part of that video where they talking about wearing a student T-shirt. It's goofy, but been exposed enough of the statistics that I kind of find that stuff funny. We use T-test when we only have 2 independent variables. Again, I'm going to try to give you an example of T-test in just a little bit. So let's just go over overview of this, and I'll give you an example. We have 3 different T-tests. The first T-test is a T-test between a sample and a population mean. We use this T-test when we actually know the mean of a population. Now this T-test is not used a lot because we don't know the mean for most of our populations in this world. Again, a population is every single individual in a particular population. So if we knew the mean for every single basketball player in the world on free throw attempts, then we can use that particular type of T-test. Well, we don't know that mean for every single basketball player and their free throw mean. So what I'm trying to get to is we don't use this particular type of T-test very frequently. We do use the next type of T-test, which is called an independent T-test. And why it's called independent, because the 2 groups are independent of one another. They have 2 different groups that are completely different than one another, and we can compare those 2 independent group means from one another to see if they are different, because again, we're trying to tell differences between 2 different groups. Now a dependent T-test is where we have 2 groups where the scores are matched somehow on one or more different characteristic. We'll actually use the second type of T-test, dependent T-test, whereas one group is tested twice. So we have a pre-test and we post-test them. And that's the example that we're going to show. Alright, so I'm going to give you an example of an independent t-test. This comes out of our textbook in page 147. If you want to read that, follow along. I've tried to give you language that I want us to use in this class. So I developed a research question. And a research question, what are the effects of intensity of training on cardiorespiratory endurance? So our independent variables, we have two of them, is the intensity of training. We have two groups. We have 40% of VO2 max and 70% of VO2 max. Our subjects are going to train for 30 minutes, 3 times per week. Both groups will do that. Just the intensity will be different. Their heart rate will be different. We'll calculate their heart rate, one at 40% and one at 70%, and those groups of individuals will train at that different level, for 30 minutes, 3 times per week. Then our dependent variable is cardiorespiratory endurance, and that's going to be measured a distance a person runs in 12 minutes. So at the end of the training for 30 minutes, 3 times per week for both groups, and I think we did this for a month. I don't remember what the book says off the top of my head, so we'll just say a month. So they train for a month, then we test them. We do the 12-minute run, see how many meters they run. We have a null hypothesis that says there will be no significant differences between the different levels of intensity of training on cardiorespiratory endurance. Okay, no difference. But we're going to use a statistical test to determine if these two groups are different from each other. In the t-test that before we get to the t-test, let's look at the group mean scores, or our descriptive statistics for this study. We have a little chart here. We have group A, or group 1, that's the 70% of VO2 max, and group 2 is the 40% of VO2 max. The N means the number of participants. We had equal numbers, so we had 15 subjects in each group. The mean score, the mean average or mean scores for this group. Group 1 ran about 3,004 meters with a standard deviation of 114 meters in the 12 minutes. Whereas Group 2 ran 2,456 meters in the 12 minutes with a standard deviation of 103 meters. Now, just looking at that, without even looking at a statistical test, we would assume or guess that Group 1, the 70% of their VO2 max, actually did better than they did do better than the Group 2, the 40%, just by looking at this descriptive statistics. But that we cannot say if the 70% was significantly better than the 40% by just looking at these numbers. We have to run a statistical test to infer that intensity actually makes a difference on cardiorespiratory fitness. So we run or calculate a independent t-test. And again, if you want to know more about the math, it's in the textbook. But the scores there, it's T. And what that 28 is, that is called the degrees of freedom. And basically that is the number of subjects minus 2. And that's how we get 28. The T equals 13.81. Now what the heck's that mean? That's just a calculation of the score. And how we determine if that is a critical number, if it's a significant number, if those two groups are different from each other, we have to use a critical values table that is found in the textbook in table 5.A on page 413. If you look at the table, if you go ahead and pause your this recording and get your book and turn to page 413 in your textbook. I'll kind of try to explain this if you got your books open, you'll see that you have on the top of it table 5.a critical values of T. You have levels of significance for a one-tailed test, 0.10 all the way to 0.0005. Then below that I have level of significance for a two-tailed test. One-tailed test is that you're assuming that the difference between a group will only go one direction. It's not used too much. You just have, if on those type of tests, you know that there's only going to be a positive change. And we don't always know that, so most of the time we use level of significance for a two-tailed test. That means that you're assuming that direction of change can be either in a positive or a negative direction. So that's what we're going to use. So that would be the numbers right below that where it says level of significance for a two-tailed test. When it starts, it has DF, that means degrees of freedom going down. That would be on the column going down. And the column, the rows on the top starts with a 0.20, goes over to 0.001. Now how we find out the critical value is that we need to find the degrees of freedom for number 28. So we go down, find 28, and then we go across. We're looking for 0.05 because that's the alpha level we set. It's 0.05, so we go over 0.05 for a two-tailed test. For 28 degrees of freedom is 2. Ooh, I put the wrong number down. Sorry about that. 2.048. My bad. Again, degrees of freedom of 28 is 2.048. It's not going to hurt us that bad. I just typed it in wrong. So since our T is equal to 13.81, it is greater than, man, I screwed up numbers all over the place, 2.048. We reject the null hypothesis. 2.048 is the number that should be in a critical value in the based on table 5.A. The critical value is saying that that number that the statisticians have calculated is a number that's at the 0.05 level. That number is saying that if that number 13.81 is greater than that, that means that there's differences between 70% and 40% in cardiorespiratory fitness in this case. So we reject the null hypothesis. Sorry about screwing the numbers up. After we've done that, we run the test. We have to answer the research question. And from the textbook, and I kind of wrote this. Table 1 reveals that the 70% intensity of training allowed students to run significantly further, give this descriptive statistics when you make remarks like that, than did the 40% intensity of training, give the means again, then and the parentheses with the T value, because that's the test. We always need to put our statistical test, report the statistical test, report a descriptive means, descriptive data. So in the end, what we learned is that intensity of training does make a difference on cardiorespiratory fitness. This test, or this study, allowed us to see that the greater the intensity level, greater the cardiorespiratory fitness. We didn't prove this. Now I want to make sure that everybody's clear on this. We're not proving anything. All we are doing is lending support for a hypothesis. We're lending support for an ideal. In science, we don't prove anything. There's very few truths in science. And there are things that we believe that are true, but we are just trying to lend support for an ideal. We are building further evidence of something that may eventually be shown to be true, sort of like the law of gravity. We have very few laws in the scientific world, so we're lending support that intensity of training gives rise to greater cardiorespiratory fitness. All right, Right, so that's an independent t-test. We have an independent, the two groups are independent or separate from one another. They're not linked in any way. Now the next one is a dependent t-test. And we're going to use another example from what we talked about last week that you guys did a learning activity on. We'll go through this again and further explain it. So a physician is evaluating a new diet for her male patients with a family history of heart disease. With a family history of heart disease. Well, sorry about that. To test the effectiveness of this diet, 16 patients are placed on a diet for 6 months. Their triglyceride levels and weights are measured before and after the study. And a physician wants to know if either set of measurements has changed. So our research question is, will a 6-month diet have a significant effect on 16 male patients with a family history of heart disease, triglyceride levels, and weight? And that's our research question. Our null hypothesis is there will be no significant differences between the triglyceride levels and weights for the 16 male patients with a family history of heart disease after the 6-month diet. So with this particular study, we have a pre-test and we have a post-test. The patients will be measured. Their weights and the triglyceride levels were measured before the 6 months, right at the beginning of the 6 months diet. They did whatever diet they did for 6 months. Then after the 6 months, they did a post-test where they measured the 16 patients' triglyceride levels and their weights. So we've seen these results before. So now hopefully got a better understanding what they did. And they pre-tested, post-tested them. We have the mean values in the top for their pre and post-test for the triglycerides and weights. And I could spend a lot of time on this because we talked about this last week. The key values again are these t-scores down at the bottom where it says pair sample test. That means dependent t-test. We have the t-value for the triglycerides. If a t equals 1.202 with a significant level of 0.248, and the weight levels, t-score is 12.071 with a significant level of 0. So again, we always need to answer our research question. The first couple bullets here are the describing the descriptive statistics. Post-diet triglyceride measures were lower than pre-diet triglyceride levels for a mean difference of 15.56 for these patients. So the triglyceride levels went down. They went down about 15 and a half, whatever they measured it in. Now the weights, the post-diet weight was lower than the pre-diet weight for a mean weight difference of about 6, maybe 7 pounds, 6.81 pounds for these patients. Okay, so that's the descriptive statistics. The next bullet there is answering the research question. It was found that there were significant differences in the pre and the post weights, the post diet weights. And the T again, that's the statistical test that we need to report. But there were not significant differences in the triglyceride levels for these patients at an alpha level of 0.05. And the so what, we always need to answer the so what. What's it mean? Who cares? At the end of everything, we need to answer the so what. The 6-month diet gave rise to an increase in a decrease in weight for these 16 male patients with a family history of heart disease, but it did not make a significant decrease in their triglyceride levels for these particular subjects. Can we infer this back to the generalized population of male patients with heart disease, can we, it's called generalize the results of this study back to people who have the history of a family history of heart disease. That's what we mean by we infer, or we use inferential statistics. We aren't making inferences or generalizations back to our population. Can we say that every single individual who goes on this diet who has a family history of heart disease will have a significant decrease in their weight, but their triglyceride levels will go down? We may be able to, but we have such a small sample population. We only have 16 people. Probably not too strong at this point. We'd have to get more subjects to have greater numbers in our population. But for these individuals, that's what happened. In a lot of your research studies, that's kind of the language that you're going to use for these, whatever you use, that had this result. And the reason why we may not be able to generalize is because of these problems that we had in our study, and we'll get into that with our research methods. So that's T-test. We just have two independent variables.